In this video, we're going to discuss hybridization theory. Hybridization theory allows us to understand how atomic orbitals give rise to shapes such as trigonal planar molecules or tetrahedral molecules, for example. Before we get into hybridization theory, it's going to be a good idea to review our atomic orbitals, because our atomic orbitals are going to be used to build what we will call our hybrid orbitals. You may remember that we have s orbitals that are spherically shaped. There are also, for any subshell, there's going to be 3 p orbitals. And those 3 p orbitals will either orient themselves along the x-axis, in which case we'd call it a px orbital. It would be oriented along the y-axis, in which case we'd call that a py orbital. Or it could be oriented along the z-axis, which would be straight up and down this way. And there'd be a lobe up above the plane of the paper and a lobe down below the plane of the paper. We'd call that the pz orbital. I'll just denote that here by drawing the z-axis this way in the plane of the paper. And we'll draw the p orbital like this, and we'll call that a pz orbital. There are also some d orbitals that we're going to need to review. There's the dz squared d orbital, in which, if we take the z-axis, there's a double lobe that sort of looks like a p orbital. And then there's a donut shape that sort of runs around that p-type orbital. I should say that p-shaped type orbital. There's another d orbital that we'll need to use, and that's going to be what's called the dx squared minus y squared orbital. And that'll have 4 lobes, 2 of which run along the y-axis and 2 of which run along the x-axis. This is normally the way we think of d orbitals, having 4 lobes. And the other 3 d orbitals look similar to this. So if you think about it, it may seem weird. How in the world can we, for example, get a shape of a molecule such as this from these particular atomic orbitals? And hybridization allows us to talk about how that happens. So we're going to talk about hybridizations for the various steric numbers that we come up with. And remember, we can have a steric number of 2, we can have a steric number of 3, a steric number of 4, a steric number of 5, or a steric number of 6. And if you recall, for example, a steric number of 6, you end up getting a molecular shape that ends up having lobes pointing in the direction of an octahedron. Or if s equals 3, we end up having a trigonal planar arrangement of electrons around a central atom. So we'll just write the various geometries that is associated. And these are electronic geometries that are associated with each steric number. With s equals 2, that's linear. With s equals 3, that's trigonal planar. If s equals 4, it's tetrahedral. If s equals 5, it's trigonal bipyramidal. And if s equals 6, it's octahedral. And I want to stress that these are electronic geometries. Remember, we get molecular geometries by first determining what the electronic geometry is. Each of these particular steric numbers is going to have associated with it a particular hybridization that we're going to cover in a bit. And here are the following hybridizations that will result in these following electronic geometries. So if we have s equals 2, we end up getting what's called an sp hybridization of the atomic orbitals. And this just means that we're going to mix or hybridize an s orbital or a p orbital, both of which come from the central atom. If we have a steric number of 3, then our hybridization on a atom with a a steric number of 3, we're going to get an sp2 hybridization. And what that means is, say in this arrangement, the central atom is going to have one of its s orbitals and 2 of its p orbitals mix or hybridize to form an sp2 hybridized atom. If the steric number is 4, we end up with a tetrahedral arrangement of electrons around the central atom. And in order to achieve that tetrahedral arrangement of electrons around the central atom, we find that the central atom needs to have one of its s orbitals and 3 of its p orbitals mix or hybridize to form what we call an sp3 hybridized arrangement on our central atom. For a steric number 5, we hybridize an s orbital, 3 p orbitals, and a single d orbital on the central atom to get what's called an sp3d hybridized atom. And in the case of steric number 6, the central atom has a s orbital, 3 p orbitals, and 2 d orbitals to form hybridization on the central atom that's known as sp3d2. So what in the world's going on with this hybridization business? Well, let's take a molecule like BeCl2, the Lewis structure for which looks like this. And we can look at this and we can say, well, the steric number on our central beryllium, that's going to be 2 atoms attached, a chlorine and a chlorine, and no lone pairs, so we're going to have a steric number of 2. In the case of a steric number of 2, we get a linear electronic geometry, and that's what I've drawn here with the Lewis structure. And we also find that our central atom, in this case the beryllium, is going to be what we call sp hybridized. And what that means is the central beryllium, its s orbital, will mix with one of its p orbitals. And when that happens, you end up getting 2 sp2 hybrids. Sp hybrids, I should say. And those sp hybrids are going to look a little bit like this. Big lobe and a tiny lobe back behind. And these sp hybrids point at 180 degrees to one another. So you notice you mix an s orbital and a p orbital. You mix 2 atomic orbitals, so 2 atomic orbitals. And what you end up getting are 2 sp hybrid orbitals that happen to point at 180 degrees to one another. And so you get the beryllium with a lobe that points this way and a lobe that points this way, and these lobes are then going to interact with the orbitals on the chlorines in a certain way. And that's basically the idea for how sp hybridization works for a steric number of 2 to give you a linear arrangement of what we call sp hybrid orbitals. What about the case where we get a steric number of 3, such as in BH3? BH3 is going to have a Lewis structure that looks like this. Its steric number is going to be, well, there's 3 atoms attached and no lone pairs on my central boron. So we're going to have a steric number of 3. If we look at our chart, for a steric number of 3, we recognize that the atoms are going to the electron pairs are going to arrange themselves in a trigonal planar arrangement around the central atom. And that trigonal planar arrangement of electrons is going to result from sp2 hybridization of orbitals on our central boron. And here's the way that's going to work. In the case of sp2 hybridization, which is always going to result in a trigonal planar arrangement of electron pairs, we're going to hybridize a single s orbital and 2 of the p orbitals, 2 of them. And one of them will remain unhybridized, because remember, there's always 3 p orbitals. Well, if this happens, what ends up occurring is you get 3 sp2 hybrid orbitals that point, oh, that's a little off, it's not too bad, that point to the corners of an equilateral triangle in a trigonal planar arrangement. So what you notice here is you take 3 atomic orbitals, and what you end up with are 3 hybrid orbitals, all of which point to the corners of an equilateral triangle with 120 degrees in between them. And this is the basis for how the trigonal planar arrangement ends up occurring in BH3. That's where we end up getting, the central boron we would say is Sp2 hybridized. Now let's look at the case where we have a steric number 4, such as an ammonia. So ammonia, the Lewis structure for ammonia looks like this. And we'd say that the steric number for ammonia is going to be 4 because the central nitrogen is, the nitrogen on the ammonia is going to have a steric number 4 because that nitrogen is attached to 3 atoms and there's 1 lone pair. That gives us a steric number 4. If you have a steric number 4, those electrons are going to orient themselves in a tetrahedral arrangement like this. And that's going to occur from what is known as Sp3 hybridization on the central nitrogen. Let's see how that works out. On Sp3 hybridization, what's going to happen is you're going to take your central nitrogen, that's right, and you're going to take an s orbital on the nitrogen, and you're going to take the 3 p orbitals, so px, py, be oriented this way. Of course, pz is going to be up and down this way, but I'm just going to draw it this way. So I'm going to add 1, 2, 3, 4 atomic orbitals, and you add them together. And when you add them together, you're going to get 4 Sp3 hybrid orbitals. And I'm going to use our method of drawing in the plane because, I really need to try to draw this 3-dimensional structure. But we're going to draw it in the plane here. So I'm going to have my central nitrogen, and then they're going to have 2 pairs of electrons coming out of the plane of the paper toward you, 1 going back behind you, and then 1 in the plane of the paper with the nitrogen. And in this case, we're going to have those lobes is going to go like this. So 2 coming out towards you, 1 of them is going to be going back behind you, and then there's a lobe that goes straight up and down in the plane of the paper. And on these 3 on the ground, or on the bottom, we're going to go ahead and put hydrogens here, and then we'd stick the lone pair here in the plane of the paper. And in this case, your 4 Sp3 hybrid orbitals that form, they're going to point to the corners of a tetrahedron with roughly 109.5 degree angles between them. Of course, it'll be a little smaller than this because this lone pair exerts a little more pressure on the bond pairs. In the case of a steric number 5, so we'll say S equals 5, that'd be a molecule like SF4, the Lewis structure for which is going to look like this. So if I was going to calculate the Lewis structure for SF4, I'd say, well, there's 4 atoms attached, and there's going to be 1 lone pair for a total steric number of 5. If we look at our chart, we recognize that the pairs of electrons around a central sulfur in SF4 are going to take on a trigonal bipyramidal arrangement, and that's going to arise from Sp3 hybridization. So what occurs in Sp3 hybridization, you take an s orbital, and we're going to mix that with 3 of the p orbitals. That's all we get. You only get 3 p orbitals in any subshell, and then we're going to add in 1 of the d orbitals. In this case, we're going to add in the dz squared. And we take those 5 atomic orbitals, and we add them together. We're going to get 5 Sp3 hybrid orbitals. And those are going to point, those 5 hybrid orbitals are going to point to the corners of a trigonal bipyramid. And I'm going to do my best to draw that here. Let's try that on a new sheet of paper. let's see, I'm going to draw sort of a hatched triangle like this. And these are going to represent the 3 equatorial positions in the sort of the equatorial plane. And then we're going to have bond going, or I should say a pair of electrons going straight up and a pair going straight down like this. And these are going to represent axial positions in our trigonal bipyramid. We're one of the pyramids. This is the apex of one of the pyramids, and this would be the apex of the other pyramid pointing down. And those 5 Sp3 hybrid orbitals are going to point to the corners of this trigonal bipyramid, which I'm going to try to draw. It's going to look terrible. We're going to try to draw it in anyway, like this. So these are 3 hybrid orbitals pointing, if I may, pointing in the equatorial plane, in which the orientations look like a trigonal pyramid, a trigonal plane. And then there's going to be 2 axial positions, one pointing straight up and one pointing straight down from this. So you can have one Sp3D hybrid pointing this way and one Sp3 hybrid pointing this way. Boy, that looks really rough. But nevertheless, this is going to be the arrangement that you're going to end up with in Sp3D hybridization. And one of these is going to occupy a lone pair, and the others are going to have the fluorine atoms attached. And so while the orientation of all of the hybrid orbitals would be trigonal bipyramidal, we're going to remember that the molecular shape in this case would be seesaw, because one of these positions is located with a lone pair. In other words, one of these hybrid orbitals, one of the Sp3D hybrid orbitals, is going to be occupied with a lone pair. Finally, we're going to look at the case where S equals 6, the steric number is 6. And so that'd be a molecule like Xe xenon tetrafluoride, the Lewis structure of which would look like this. Yeah. And if we were going to calculate the steric number for this xenon, we'd say, well, there's going to be 4 atoms attached, a fluorine, a fluorine, a fluorine, a fluorine, and there's 2 lone pairs. So that's going to be a steric number of 6. In this case, if we look at something with a steric number 6, it's going to have an octahedral electronic geometry surrounding the central xenon. And the hybridization is going to be Sp3D2, which means we're going to have to hybridize an s orbital on the central xenon, 3 p orbitals on the central xenon, so 3 p orbitals, and we're also going to have to mix in 2 of the d orbitals. It's going to be dz squared, and dx squared minus y squared is what we're going to end up putting in. So 2 of the d orbitals. So we're going to mix all that in, an s, 3 p's, and 2 d's. So we're going to mix 6 atomic orbitals on the xenon. And what we're going to get out is 6 hybrid orbitals. I should say 6 Sp3D2 hybrid orbitals that are going to point to the corners of an octahedron. We'll go ahead and draw that. It'll be a little easier to draw. Just draw our hatched square like this. There's central xenon, and then there's a position going up and a position going down. And these Sp3D2 hybrid orbitals are all going to point to the corners of our octahedron. All 6 of them. And then the fluorine atoms would come in and they'd overlap. In this case, they'd overlap here, 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 and here, whereas you'd have lone pairs at these 2 positions. So while you'd have an octahedral arrangement of your Sp3D2 hybrid orbitals, the shape of the molecule, if we you ignore the lone pairs, the shape of the molecule, we'd call it square planar. I suggest that you, if you want to visualize this a little further, you go to the web address listed on slide 27 of PowerPoint 8B, and this allows you to look this process over in video detail.